membrane of the vesicle fuses with the membrane of the axon terminal, enabling the vesicle to release its contents into the synaptic space. The molecules released from the vesicles are chemicals called neurotransmitters. They drift across the synaptic space and bind to special proteins called receptors on the postsynaptic neuron. The binding of a neurotransmitter to its receptor can trigger an action potential in the postsynaptic neuron. That electrical signal then moves toward the cell body of the postsynaptic neuron. Now that the neurotransmitter has relayed its message, it releases from the receptor into the synaptic space. Some of the neurotransmitter is degraded by enzymes in the synaptic space, and some of the neurotransmitter is carried back into the presynaptic neuron through transporter proteins. The neurotransmitter that is taken back up into the presynaptic neuron is then repackaged into vesicles that can be released the next time an action potential reaches the axon terminal. The entire process repeats each time an action potential reaches the axon terminal of the presynaptic neuron.
So when we get to the end of the PowerPoint, then we're going to talk about like depression and schizophrenia. So first, let's get through this, and then we can have a cool discussion on that. Okay. To summarize, and you know I like to draw beautiful pictures of the things that we talk about in class. So I want you guys to do the same thing on your paper. You don't have to, but it's nice to get your own visual going. This is our presynaptic neuron. This is our postsynaptic neuron. This is our axon of the presynaptic neuron. This is the dendrite of the postsynaptic neuron. I mean, this is the part that receives an impulse. So, just like with the muscular system, an impulse reaches the end of the axon. So it gets to the axon terminal. When it reaches the synaptic knob, that's what they call it, we're going to add in a detail that we didn't talk about in muscular system. There are these tiny little channels on the neuron. They're a little bit different. And these channels are going to introduce calcium into the neuron, to the presynaptic neuron. So it's just an extra step. Before before the neuron can release its neurotransmitter, calcium has to enter that axon terminal first. Okay, so that would be the second step. This leads to, you can think about it like the calcium pushes out these vesicles. So these vesicles are storing neurotransmitter, and we're not saying acetylcholine because it's not always acetylcholine. It is in the muscular system, but not in the nervous system. We could have serotonin, we could have dopamine, we could have epinephrine. But in this circumstance, we're just going to call it neurotransmitter. It's kicked out of the axon terminal and binds to the receptors. That is step 4. The neurotransmitter binds to channels or receptors and exerts either an excitatory effect on that neuron or an inhibitory effect on that neuron. Okay, so how would it do that? Does anybody have any ideas? We know already that a neurotransmitter can bind to a channel and open it up. When that channel is open, remember what ion is hanging out outside, just waiting to charge up? It's going to be sodium. Remember, sodium's hanging out, waiting for that channel to open up. Okay. Once that channel is open, that sodium is going to rush in. That's an excitatory response, meaning we're exciting that next neuron with sodium. Okay, but how might this process inhibit the next neuron? it could close the sodium channel. If we close that door, then it's going to be a lot harder to excite this neuron. So that's how we can exert either an excitatory generally opens channels, or an inhibitory signal, which closes channels. Why would we want to inhibit neurons? That doesn't make sense, does it? Yeah.
If there's an overstimulus, it
Yeah.
would blow off the action potential. So there's that special like bell curve like diagram of the action potential. There's a point where after it has gone through its apotheosis or its zenith point, when it gets to the highest point in that graph, that's when it's causing a reaction. But then there's a point where it dips very low, like negative 70, negative 75. If it goes below that, it can cause an issue. It could cause like maybe the muscle to spasm or to, well, not the muscle, but the nerve itself to have a problem. So it has to be very precise in order to prevent too many ions from coming in and giving us like a fake charge or a fake reaction.
Okay, so we can do this to prevent overstimulation, right? Is that what you're saying? Yeah, so we can, we can shut neurons down in order to prevent, over responding, or hyper response to something. Correct. So, what else? When we're sleeping, right? Well, you would want to release inhibitory signals in the brain, right, to shut things down. That's another one. Yeah, pain, to shut down pain. You want to release inhibitory substances, neurotransmitters. So that's why in the nervous system, in order to do that, we have neurotransmitters we use to excite neurons, and then we have other ones. That's why we didn't name this one, because this could be a neurotransmitter that excites another neuron, like dopamine. Dopamine is an excitatory neurotransmitter. It makes you happy. Okay, it opens up sodium channels and excites the brain. Melatonin calms down the brain. Okay, so that's a neurotransmitter that causes an inhibitory effect. So that step 4 is really important, right? Because that's kind of defining the nervous system, is either being inhibitory or excitatory. Okay, so let's talk a little bit more about that signal. Cell membrane is usually electrically charged or polarized, so that the inside of the membrane is experiencing a negative voltage at rest. The reason that a neuron is negatively charged inside at rest is because more potassium is hanging out outside the neuron. So if you've got a positively charged ion and you push a bunch of it out of the neuron, the outside of the cell is going to be much more positively charged than the inside. So that's going to cause an unequal charge, meaning the inside of the neuron is going to be at negative 70 millivolts. That is the resting potential of a neuron. So maybe somewhere in Learn Smart last night, it asked you about resting potential of a neuron is negative 70. That's your magic number. So neurons begin, or at rest, are at negative 70 millivolts. Okay, so this is just the cell membrane of a neuron. This is the outside, this is the inside here. More sodium. Remember, sodium is positively charged. More sodium is hanging out here than in here. Does anybody know why? How did that happen? There's a pump in the membrane right here. Good. That purple thing is a pump that keeps bailing sodium out of the neuron, pushing it outside. It's almost like if water were entering, if there are a bunch of holes in your canoe and water is coming in, okay, you have to constantly bail out the water out of your canoe. That neuron is always doing that. So this specialized channel is called the sodium-potassium pump, and it constantly sends sodium out. I'm going to erase some of these other ones so that we can get a better sodium-potassium pump, and then it pulls potassium in. So it's constantly sending sodium out and potassium in. This pump is responsible for maintaining the negative 70 resting potential of every neuron in the body. That's because sodium is a more powerful ion. So it's pumping out a ton of sodium, which eventually gets us to that negative 70 voltage. So once again, you want to think of it like a canoe situation. To keep your canoe afloat, you have to continue to bail water out of your canoe, and that neuron spends a lot of time, you spend a lot of energy doing that, but you're going to stay afloat. That neuron spends a ton of time just taking sodium and sending it out of the neuron. It spends a lot of energy on it, ATP as well, so that it can reach this magic number. Yeah?
In the Kruger picture thing, is it like once a potential, actual potential goes through, the nerve is more responsive with higher voltage molecules, or more positively charged molecules?
Let me make sure I understand your question.
So like, let's say an actual potential comes through and then the actual sodium outside, the nerve that it's sending the potential to is more likely to respond quicker with more voltage going through it.
So you mean it's put at like a certain level to allow it to respond more quickly? It's put at that voltage? Or are you talking about because there's more sodium outside?
Yeah, because there's more sodium outside, so like whether it was -7 or negative something,
Yeah.
when there's more positive charges outside,
Right.
the potential goes through.
Yeah. It
It's
sets it
in
up
a
for a
deficit,
quick.
so it needs, like, it's gonna respond, I'm assuming it will respond faster to the positive charge.
Yeah, that makes more sense. So it's a way to like, it's a way to kind of make nerve signals travel more quickly as you keep the sodium outside, and it's just waiting to rush in.
Right, kinda like those marathons or the swimmers, there's one waiting, and there's one coming at him,
It's like a relay.
and he starts running and then just takes off.
Right, yeah.
Maybe.
Yeah, that's a good way to think about it. I mean, if that helps you understand the negative sodium voltage, that's good.
But, like, I just wanna understand the bigger picture, is that a possible thing, or is it just?
More so, I would say, like you're kind of getting to the right answer, but the like what a textbook will say is it will say, okay, a difference in charge allows for something to happen. So you remember when we were talking about gradients?
Yeah.
Remember about the gradient inside the mitochondria, since we have all this hydrogen inside the mitochondria waiting to get out. As soon as it's given that escape route, it rushes through and powers that channel to create ATP. It's the same concept. Anytime you have an unequal distribution, you got potential energy. Does that make sense?
That makes sense.
Yeah, so you're kind of getting there. That's like the general, I would say like the big picture is anytime we have an unequal charge, we have the potential there for energy. Yeah, makes sense. Cool. All right. Question. Does that make sense, guys? It's like if you have that's how batteries work. Batteries hold. The way that a battery works is that you know how you got two sides to a battery. I had a dream about batteries last night. This is the wrong when. So a battery holds a positive charge on one side, where the little knob is, and a negative charge on the other side, where that other knob is. So that when you attach it to something, that charge rushes through it, and it can create energy. So it's a potential energy. It's a really interesting thing. What it's pulling is it's pulling electrons to one
I
side.
was just gonna say, that's, when you talk about potential energy, that's kind of what we're talking about, is that unequal balance.
Right.
Okay.
Right. That's kind of the point I'm trying to send home. Yeah, unequal. Okay. So that's maintained by the sodium potassium pump. There are other ion channels in the membrane though. That's not the only ion channel in the membrane. That's like a dual wielding ion channel. Okay, for any of you gamers out there. In terms of like single wielding ion channels, you've got sodium channels and you have potassium channels that only pump sodium and only pump potassium. That one just happens to do both. We talked about the resting membrane potential. It's a negative 70. That means there's a difference from the inside to the outside of the cell of negative 70 millivolts. That means the nerve is polarized. Remember, polarity is a difference in charge from one side of an atom to another. It's the same thing with a membrane. This is a polarized membrane. More sodium hangs out outside the cell. And more potassium hangs out inside the cell. And this is the kicker here. More negatively charged ions and proteins hang out inside the cell. So think about this really quickly. You've got positive sodium out here. You've got positive potassium. Potassium inside. And then you add a bunch more negatively charged molecules inside the cell. You're going to reach that negative 70 millivolts, okay, which is what we need to be at. If the resting potential changes, remember, you're constantly bailing water out of your canoe. That sodium potassium pump is constantly working. So if anything changes, it's going to be brought back to baseline really quickly through that sodium potassium pump. You can watch videos. It's good to watch videos on YouTube. You can watch videos on YouTube of the sodium potassium pump and actually get a visual of how it's working. Keep in mind that this charge is maintained throughout the entire surface of the cell membrane. That's what this diagram is showing you, a bunch of negative signs inside the cell, a bunch of positives outside the cell. And then one pump here working, pumps sodium out and potassium in to maintain a high concentration of sodium outside and a high concentration of potassium inside. And keep in mind, it's not just right there. We have pumps distributed throughout the entire cell membrane doing this all the time.
That kind of makes more sense with the battery,
Yeah.
negative and outside and positive inside.
Right.
And once you need to charge. Right.
Yeah, it's potential energy. Yeah. Once you hook up, a toy, the battery to a toy, that toy starts to move. It's the same thing with the nervous system.
And where the toy?
Yeah. Exactly. Okay, more definitions. If a cell becomes more negative, it becomes hyperpolarized. If a cell becomes more positive inside, we're talking about the voltage inside the neuron. If it goes down to negative 80, negative 90, negative 100, we call that hyperpolarized, meaning more negative. If the charge inside the neuron starts to rise up to negative 60, negative 50, up into the positives, we say that's a depolarization. The threshold potential, this is also another magic number, is negative 55. Once a neuron, here's a chart of the voltage, okay? Once a neuron goes from negative 70 and hits negative 55, that begins a nerve impulse. It's at that specific point where we reach threshold. Okay? Kind of like everybody has their own little threshold, right? Especially if you have like an older brother or younger brother. Everybody's got their own threshold potential, right? It doesn't really change over time. It's that same threshold that stays the same. After that point, that's the freak out moment. Okay, so for a neuron, that's the freak out moment, is negative 55 millivolts. That can be accomplished by, think about charges. That can be accomplished by the proper amount of sodium entering the neuron at the synapse. Right? So if enough of these sodium channels are open, enough positively charged sodium goes in and will stimulate that nerve as long as it gets to negative 55. That's called a depolarization. And that causes an action potential. This is what an action potential looks like on a graph. So you're going to see all of our values on this graph. You're going to see negative 70 is the starting value. Okay, so here's our millivolts on this side. Here's our time in milliseconds here. So this is really fast. This happens really quickly. Negative 70 is your starting voltage. And that's also known as your resting potential. Once that neuron gets hit with enough sodium or excitatory neurotransmitter, and it gets to, what's that number again? Negative 55, then the threshold is reached, freak out moment occurs, okay, and we shoot all the way up to positive 30 every time, okay? So you throw the same punch at the same velocity at your sibling every time you hit that threshold. Okay, it doesn't get any better or worse. At least mine didn't. And then I have an older brother, by the way, just this is where these references come from. Okay, and then as soon as it hits positive 30, it undergoes a uniform recharge. Okay, so the upshoot is called depolarization. Remember, depolarization means, this is weird, less negative. D means less, polarization is negative. So that means we're going into the positive range. And then once we hit positive 30, swoops back down. That's called repolarization. That's easier because it means more negative. Recharging. So we're going back down towards our resting potential. And we actually go a little too far. Okay? That's the apologizing moment. I apologize for that. And now we're going back up. So it's about like negative 80, negative 85. And then it comes back up and is restored to negative 70 because this thing's always working to restore negative 70 charge. Yeah, Jamie, go ahead.
What did you call the positive 30 at the top, where it goes from depolarization to repolarization?
Oh yeah, it doesn't have a name. It's just sort
Is
of.
that just like another threshold that it just meets? And then
Yeah,
just-
that's the voltage that it ends up at. That's just the peak, or the apex. And so this is uniform, meaning every time a nerve fires, every time that proper amount of sodium gets into that neuron, it experiences the same exact charge pattern. It's kind of like an EKG, right? If you get a reading of your heart, you get that dee, dee, and you see the P wave, the QRS, and then the T wave. That's the same thing. It's uniform for everybody's heart all the time. It's the same voltage, unless there's some sort of issue. Yeah, it should be. Yeah.
Yes, when this threshold number is reached, I know it's easier to think about in terms of like muscle, maybe like on like an effector response, like an effector performing an action to kind of, I guess, repolarize. But could this result to things like eye blinking or heart rate or digesting? Like, what would be some of the odd mechanisms that the neuron will try to do if it's not appropriate to send a muscle response to try to regain its polarity?
I didn't follow your.
Okay.
I didn't follow your question. Sorry, I'll have to
So
ask that.
if a neuron becomes if it becomes too loses its polarity to beyond that negative 55,
Up or down?
it would be, I'm gonna say up.
Okay,
Yeah,
so
yeah.
it goes closer to threshold? Okay.
If it can't do a regular mechanism to regain its stability, what irregular mechanism will it do?
I still don't understand.
I'm just thinking like, it has a certain way of doing this to keep itself in check. And what would be the irregular way of doing it? for someone who has seizures or has an issue, a class issue,
Okay.
a traditional issue with this.
So what would be a problem with it?
Well,
Is that what you're asking?
But I'm also thinking of the solution to the problem. Like, how would irregularity result to a solution to take care of it, or at least just stabilize it?
I still don't understand your question. I'm sorry.
It's okay.
Maybe ask me after class to get the right words. Okay. I understand. Okay, it doesn't always come out the way you want it to, right?
I'm
Yeah.
thinking of something very particular.
Okay, yeah, talk to me afterwards, we can do that. One interesting thing that happened in a movie, I always like to do movie things, is James Bond in Casino Royale experienced a heart attack. Well, it wasn't really a heart attack, but his heart stopped because he got poisoned with digitalis. Okay, so like that scene where he's at the poker table and he takes a drink and he's like, oh crap, something's wrong. He drank digitalis, which is a heart medication used in small doses, but he got a lot of it, and it stops this sodium potassium pump. So if you can imagine the results of stopping the sodium potassium pump, maybe this kind of might answer your question. If this stops, what happens?
You don't maintain that negative 70.
Yes, so you don't maintain the negative 70, and you lose the charge of all the neurons in your body. This one goes to the heart. So you lose the charge of the neurons in your heart, and you no longer have that potential energy, and everything flatlines because you can't pass electrical signals through your heart. So that's what happened to him, and that's why you had to
Reach for the defibrillator.
hook the defibrillator up.
I didn't know Aston Martin's came with defibrillators.
Yeah, they sure do. Yeah,
All of them.
Right in the glove
That's
box.
standard.
That's part of the premium plan.
Yeah, they figure you're a thrill seeker, so if you buy one.
So when someone has a heart murmur, does this work the same way? It gets overexcited sometimes when it gets.
A murmur is
Every murmur is different, so it could be electrical problem. Yeah, like a lot of times a murmur is an electrical problem, meaning, so this is representing the neurons, not just in the central nervous system, but the peripheral nervous system, and even in the heart conduction system. So you use this information again in cardiovascular system. Yeah, that's generally due to some improper wiring of the neurons of the electrical impulses going through the heart. So like if the wiring's off there and the nerve signals aren't sent properly to the heart muscle, then it's not going to beat right. And that
So if
can cause a
someone
murmur.
As a pacemaker, how do they have a heart murmur? Is that even possible? Because a pacemaker is supposed to like.
Regulate it?
Yeah.
Yeah. There's a really complex answer to that question. So if you stick around afterwards, I can answer that question.
Okay.
I can.
Yes.
You just have to
Yes.
remind me. Okay. My uncle has got a pacemaker too, so.
My dad got one when he was 35, and they just told him he had a heart murmur, and I'm like,
Yeah.
how does that work?
Yeah,
So-
everyone's a little different too, so
Yeah, I'd
we
like
talk
to.
about that.
Yeah.
Okay. Cool. Let's watch a video. So before we do that, I want to show you a circumstance where we wouldn't reach threshold. Okay, a mosquito's on your skin, and it's kind of just like traipsing around on your skin surface, and you don't feel it. But your neurons are responding. Did you know that? So you've got a few sodium channels opening due to some stimulation of that neuron, but not enough sodium channels open to get us to threshold.
So we're conscious of that.
Right. Okay, so now a tarantula is crawling on your arm. Lots of sodium channels are opening in that circumstance because that nerve is getting very stimulated by the skin surface. Okay, that dendrite inside the skin surface. So enough sodium channels open and you get a nerve impulse, but you probably won't just get one, you'll probably get multiple in a row. Okay, but that brings us to a good point. It's not like with a greater stimulus, the nerve impulse doesn't get stronger. It doesn't go up to positive 60, 70, 80. You just fire more of the same uniform impulse.
And it's in milliseconds, so
Right. Yeah,
it's really fast.
super fast.
Jimmy Johnson right there.
Who?
Jimmy John's.
Jimmy John's. Commercials are ridiculous. The fire department one makes me laugh.
I love that one.
Okay. Listen to a lot of radio. We have a diagram here showing you, don't forget all the sodium is hanging out outside at rest. Purple is sodium, potassium is inside, this is the axon, this is the voltage. If some, in the axon, so keep in mind, once the axon is stimulated, once that first segment of the axon is stimulated, it will always travel all the way down the axon. It's an all-in-one thing. Okay, as soon as it's sparked, it goes all the way. As soon as threshold stimulus is reached at the axon hillock, which is the beginning of the axon, then that signal progresses down the entire length of the axon, okay, in waves. So as this segment of the axon fires, it's going to fire the next one and the next one and the next one in sequence. But as these segments are firing, the segments behind are recharging. It's kind of like the wave at a sporting event. Once your hands go up, okay, they don't stay up. Never mind. I was gonna make a bad joke. And then you put your hands back down. That's you recharging the neuron. Okay, that's the repolarization. So these are all the special numbers. Okay, these are the numbers to memorize. -55 threshold. Depolarization is towards 0. Repolarization, after we go up to +30, okay, goes back down towards your resting potential. But remember, it shoots underneath for a moment. That's hyperpolarization, which is generally at -90. What returns that neuron back to its resting potential?
The potassium.
Bailing, constantly bailing out sodium potassium pump. Okay, let's watch a video.
TV where we're making biology fun. My name is Leslie. This is episode 13 where we're going to be talking about action potential. I'm basically going to be giving you a review of the concepts that we've been talking about up to this point when it comes to the action potential. Over here we have our neuron, and the part of the neuron that we are going to be focusing on is the axon. So that's this region here, starts here, and it goes to about there. Now,
okay, so this stuff here, synaptic transmission, was at the synapse. Okay. Now, what we're talking about is once that the synapse stimulates the neuron, once we've reached threshold, now we're talking about what's happening here in the axon. Okay, so we stimulated the neuron, now we're talking about an action potential, okay, which is happening in the axon. So keep in mind where we are in the neuron, which is why I played this video.
what I'm going to do is I'm going to take a section of the neuron. So let's say I'm going to take this part here, and I am going to draw it down here. So here we have the axon. This is inside the axon, and this is outside the axon. Now, if you remember from a previous episode, outside the axon we have a lot of sodium ions. So I'm going to draw sodium ions here, and they are all outside the cell. Now let's look over here. Here we have a stimulus that's happening. And you can see there's a first stimulus that does not reach threshold, so nothing happens. Another stimulus comes, it does not reach threshold, so we still do not get an action potential. if we have a stimulus that's strong enough, and I'm gonna draw another stimulus in here. So let's say we have a stimulus that's that big. That's gonna reach the threshold and cause an action potential. When that happens, voltage-gated sodium channels are going to open, and that's gonna cause sodium to rush into the cell. Of course, that's gonna start at the axon hillock. Sodium is gonna rush in, making the membrane potential even more positive, causing more channels to open, more sodium to rush in, more sodium to rush in along the axon. What is that going to do to the membrane potential? You can see right here, this is where we get depolarization. The membrane potential goes up and up and up.
Okay, so remember how we said we have a channel here that's the sodium potassium pump, and that's always working. Okay, it's always happening. It's like bailing water out of the canoe. And then we said we have other ion channels participating. So guys, when sodium is rushing into that axon, it's only going through its own personal sodium channel. Okay. So that's why we have these other ion channels embedded in the membrane. You can almost think of it's kind of like an even distribution. Within the entirety of the axon, you know, every couple nanometers, we've got a sodium potassium pump that's always working. But then interspersed within those nanometers, we've also got just plain old sodium channels that allow that sodium in. And then we have plain old potassium channels that are going to allow potassium out. So keep in mind, those two are always going in opposite directions. If the sodium's going in, potassium's like, see you later, I'm out of here. You know, it's almost like they don't like each other. They don't like to be around each other. So then there are potassium channels for that.
Up and up, and it's trying to reach the Darwin equilibrium for sodium ions. And that equilibrium potential is somewhere around 58 millivolts.
But it never gets there. It's just trying to get to its equilibrium.
So sodium is
it only gets
rushing
to 30.
in because of the driving force causing sodium to go in. Sodium wants the membrane potential to go up to its Darwin equilibrium, and that is around 58 millivolts. At this point, voltage-gated potassium channels have enough voltage in order for them to open. So I'm going to erase all of this now, and we're going to take a look at the axon again. I'm going to draw it here in blue. And inside the cell, we have a bunch of potassium ions. Now we have such a positive charge on the inside that potassium ions want to leave because positive repels positive. When voltage-gated potassium channels open, potassium can now leave the cell. So we have a lot of positive leaving the cell, and what that is going to do is cause repolarization where the membrane potential is going down. Just like with sodium, potassium wants to reach its equilibrium potential, which is somewhere around negative 93 millivolts. And that is why the membrane potential is going down as it's leaving, because potassium wants the membrane potential to be at negative 93 millivolts. That is where it is most comfortable. Considering that the resting membrane potential is around negative 70, the membrane potential goes significantly lower than that negative 70, and this phase we call hyperpolarization. All along this process, we have the sodium-potassium pumps that are pumping sodium out of the cell, 3 sodium ions out, and 2 potassium ions back in. And that's going to cause the membrane potential to eventually reach back to its resting state. This is the entire action potential, looking at depolarization, repolarization, hyperpolarization,
So what you want to do
and getting
is, this is what I would do. and this is what I did when I was studying this stuff, is I drew out this graph and I labeled the resting area, the depolarization, the repolarization, and the hyperpolarization. And then I drew in the physical channel that's responsible for each phase. Meaning, on this line, I drew in a sodium-potassium pump, because that's what maintains, and over here, the resting voltage. So you can go ahead and do that, and that'll help you remember what phase is dominated by what channel. So drawing your sodium-potassium pump, almost like this is a membrane here, the line. And that'll tell you the sodium-potassium pump is responsible for resting potential. And this line, if this is also a cell membrane, you would draw in a sodium channel, just the sodium channel, because sodium channels, sodium traveling through its sodium channel is dominating the depolarization phase, or causing it to go towards a positive charge.
So what are we drawing now?
A sodium channel. Just a little block. On the repolarization phase, or the down phase, you would draw in, on that line, a potassium channel, because as potassium moves out of its channel, out through its channel, that membrane is repolarizing. And then you have to know which direction the ion is going through the channel. That's easy. You just draw it going in, you draw an arrow inwards through the sodium channel. You draw an arrow outwards through the potassium channel. And then you draw opposing lines, of course, for the sodium-potassium pump. And then you have all that information on one picture. Okay, that's going to be a valuable study tool. So, in terms of the opposing lines, which one is leaving for the sodium-potassium pump? Sodium is the one going out. Potassium is the one going in. Joe, go ahead.
When it reaches hyperpolarization during the refractory period, is it kind of the same with a muscle and a neuron? Like the neuron cannot be like charged at that point?
Correct.
Because with a muscle during a refractory period, it can't
contract
it
again.
can't contract again.
Exactly. So while the repolarization is happening, okay, actually while the depolarization and the repolarization are happening, we wouldn't be able to generate another action potential until we got back to, actually, you know what? You can still generate one right here at this point. But for most of repolarization phase, you cannot regenerate another action potential. That's for safety purposes, so that you don't get this buildup of this enormous electrical charge in your axons, right?
Fry your nerves.
Huh?
And fry your nerves.
Yeah, you know, fry your nerves, or, you know, talk about seizures. Seizures are too much electrical activity that's improper firing. Yeah. That's called the refractory period. So I want you guys to check your drawings with your neighbors and make sure you have the same thing. Make sure everybody's got the same thing. And if you don't think it's right, just raise your hand. It's actually embedded within the PowerPoint, so if you just download the PowerPoint, it's going to be on there.
Okay, cool.
There'll be a link.
There's a link on it.
Oh, it's positive, positive, no.
I don't know if I watched that many times, I would probably fall asleep.
Because it only,
That guy kind of like reminds me of the guy that,
as
I forget his name, the guy that did the Pretty Little Pictures,
I don't know.
PBS.
Oh, on the outside. Yeah, I know, Bob Ross.
Bob
She's got a
Ross.
question.
Okay.
Bob Ross, I don't sleep, so he,
Yeah, what is it?
every day.
She
Yeah,
said.
that guy's voice. I was like, no, not a chance. Like, I could listen to it once and be like, alright,
Mhm.
done.
Potassium is actually leaving. So if a positive ion is leaving the inside of the cell, positive is leaving, that would become more negative. So you just have to kind of reason through it slowly. Thinking is hard. Okay, so this slide is kind of explaining the events just in text form. So I'm going to let you just read through it as you're looking at your graph and make sure everything lines up there with your values real quick. Okay, so hopefully everything lines up there. Feel free to come at me with questions after we're done. I want to show you guys the wave here as it passes. The signal is conducted down the axon. Remember, it's kind of like a wave, right? So the positive sodiums come in. That part of the segment is charged, okay? And then once it's charged, those positive sodiums then leave, and the next ones come in. And then those will leave, and the next ones come in. Okay, so it can only travel one way. There's no backtracking of nerve signals. The wave only goes one way around the stadium, okay? You won't succeed if you try to get it to turn around all on your own. It's just not gonna happen. You have to go with the rushing of the ions. So broken up into even smaller steps here, we've got impulse conduction here. So once the axon is stimulated, once again, the impulse travels its entire length. Step 8 is kind of describing that. The action potential occurs sequentially along the length of the axon. Once it gets to the end, this happens again. So now we're here again. When that impulse travels all the way to the end of the axon, now we're here, and now we have neurotransmission. So it's really just a game of neurotransmission, excitation, back to neurotransmission. Oh, we have inhibition, so now we've stopped the cycle. That means we've shut down some sort of nerve pathway, which we want to do at night or when we're sleeping, or when we're taking a test. We want to shut out all the nerves taking, trying to process signals of sounds from our environment. And we want to excite those nerves responsible for cognition in our frontal lobe. Yeah.
So, when you're shutting down for sleep and dream, are you really shutting down? Because isn't it you spend energy on dreaming, right? Because it takes energy.
For thought processing.
Yeah. And so generally I wake up tired when I dream.
So what is being shut down, right?
So is there actually shutting down everything?
Yeah, in
To some extent, I guess.
Yeah, remember all those connections just in that 1 millimeter of brain tissue? So just imagine that throughout the entire brain. So some of those connections are being shut down while others are being stimulated, specifically in your dreaming centers, right, or your memory centers are lighting up at night. That's the only time you code long-term memories is while you're sleeping. Do not code long-term memories during the day when you're awake. The portions of your brain that are the motor centers, those definitely shut down. Those are all inhibited. If they're not, then you're going to sleepwalk. Yeah.
You're dreaming about driving, you're actually.
But sleepwalking,
Oh, I hope not.
sleepwalking only happens during NREM sleep, because during REM sleep, you're almost
Awake. You're almost awake during REM sleep.
Yeah.
Yeah. So the brain patterns are mimicking wakefulness. But the things that are shut down
Or the motor.
So a lot of things in the brain are active at that point, but the motor centers are shut down, which they should.
It's creepy. I have 2 sleepwalkers.
Oh,
2 of my
do
kids,
ya?
Yeah, they've gotten up and
Generally
taken
they're
showers
kids.
and,
Yeah.
yeah.
Are they both
One's
young
in her bed.
kids?
Mm-hmm.
Yeah.
She's 13 though, and she's still, like, makes me nervous. Like,
Yeah.
they can walk outside or
That's crazy.
whatever. She'll talk to you, she makes no sense.
Wow.
It's kinda creepy,
Yeah.
actually.
That's kind of scary too. Right? Yeah, so now you know what causes it. It's, you have enough inhibition. That generally happens with kids because their brains are so active and they're just learning and they're growing and they're developing.
You're thinking about Pokemon Go.
Pokemon Go. When's the next Pokemon Go gonna pop up? The police station. Yeah.
They're gonna arrest you.
I just didn't leave my class the other day to go catch Pokemon.
Are you serious?
I was like, you can't do that. Yeah. Okay, so what's happening? I think we mentioned this, but what's happening electrically when you touch warm water versus boiling water? So it's not that impulse gets bigger. It's that you have a higher frequency of exponentials being sent per second, not a stronger impulse. All axon impulses, or action potentials, also known as, are the same strength up to positive 30 and then back down. The only difference between an elephant sitting on your chest and a mosquito on your arm is just frequency of impulses and amount of neurons stimulated, right?
Could you be the different type too? Like, because warm water is just your thermoreceptors, but boiling water is your pain receptors.
Yeah. So now you've got different types of receptors that, send signals to the spinal cord. So yeah, you're gonna get information flow through pain receptors, through thermoreceptors, through touch receptors, through pressure receptors. More neurons gonna be firing. Different types. And if they're sensory receptors, they're gonna be unipolar neurons, the unipolar type.
It's kind of funny when you mentioned an elephant sitting on your chest versus a mosquito. If you actually feel like you have an elephant sitting on your chest, you're probably having a heart attack and
Yeah.
you might want to call 911.
Yes, I agree with that. I think that's a good synopsis. I think if you have that feeling and then your left arm starts
Starts
to
to
tingle,
tingle.
and then your left jaw, neck, and you need to, yeah. It's not really an elephant, it's a heart attack.
It was just the cheesecake earlier.
Which is
I had
actually kind of,
digitalis in it.
I've actually felt that whole stimulus process, but I was actually just having a severe panic attack.
Oh, yeah.
So like the entire left side of my body went completely numb.
Yeah.
But it was just, I wasn't having a heart attack, I was just having a severe panic attack.
Yeah, a lot of people confuse the two, and they're easily confused because they have the same symptoms, sweaty, heart rate, all that stuff.
Is it a panic attack, is it like just too much dopamine? Or what's the hormone responsible for adrenaline? Adrenaline?
Well, epinephrine is, adrenaline is epinephrine, so yeah, it's this massive release of epinephrine in your body, mimicking an emergency situation. So your body just,
Is that like the fight or flight thing?
yeah, your body goes into fight or flight mode, which we'll talk about in chapter 11.
Which is what happened with your student when you went to go catch the Pokemon.
I gotta go get this Pokemon. It's an adrenaline rush, dude. Hilarious. I think it's a great game. I think it's fantastic. It gets people out of their house.
It's
They
got
don't
people
go out of their
so
house.
active.
Yeah, it gets people so active that they, you know,
I
run into traffic.
I saw a meme where it was like, took the Obama.
Yeah, it's
Yeah.
Michelle Obama so long to get young kids active, and it took
And then
Pokemon
Pokemon
Go.
Go.
Pokemon Go has done more for child obesity in 1 week than Obama's have in 8 years.
Yeah, I mean, you just never know when a novel idea is gonna just hit and be effective. It's amazing. Yeah, it's almost by
I
chance.
know
It
couples
also-
that are like going on dates just to go find Pokemon. I'm like,
Yep.
It's also promoted, I've seen a couple people like cheating at it where they'll put it on a bicycle,
Mhm.
tape it to a bicycle and spin the wheel. Cause like, you need movement
Right.
to like get things done in the game.
That's a really good idea.
And then there's another one guy that put it on his, what are those little helicopter toys?
Oh, it was a
Drone, yeah, he put it on his drone, just drove it around the yard.
Really smart, actually.
Wow.
So,
Huh.
you're exercising one part of your body, right? Make it think harder or.
Yeah, I think it's awesome, and people are actually like communicating with each other and like talking to each other again in public.
Yeah, meeting
I
people,
think
right?
that's great.
Yeah.
Yeah. You used to be able to do that, like when I was like,
Pretend it's
back when I was
1978.
younger, and like people would talk to each other in a coffee shop. You wouldn't just like be on the Wi-Fi on your phone.
You're
It was cool.
Isn't that app though powered by Google?
Huh?
Isn't the Pokemon Go app powered by Google?
Oh yeah, it is. Yeah, it's a Google.
The one
It's
one
Nintendo.
negative-
It's made by Nintendo and powered by Google.
Yeah, the one negative about that though is that if you have the app open and up,
Use
you're
all your data.
yeah, anyone can access any of your data at any point in time that you have saved on Google.
Oh.
So it opens the potential for hackers to get into your Google account.
Right.
maybe that's
Not my
Unless you're in the
science
middle of
notes.
a
So
That's
just
only
be
if you're
aware
connected
if you
to
love
Wi-Fi, right?
Pokemon Go
And love other stuff that's in your bag.
and you love other stuff that's in your that's saved in
Yeah.
your Google account, what's more important, catching the Pokemon or saving the data that's saved on your Google account?
So that's not even when you're attached to Wi-Fi. That's just in general when you're streaming data.
When yeah, I mean,
I was reading comments, they were saying that was already fixed,
I
so I don't know.
I don't
'Cause
I don't know if you can actually fix that.
My
because-
16-year-old's kind of a gamer
Yeah.
nerd, and he was like, oh, this is just the beta phase, this is just the tryout.
I mean,
They're working all
was
the bugs
Apple in
out.
the beta phase when their cloud got hacked?
Like, I don't know what you're talking about.
Okay. Good talk. Let's move on to refractory period, which is something we talked about. Remember in the downswing. So during the depolarization, there's a small period of time where you cannot generate another action potential. You can't get another one until a certain point. That's called the absolute refractory period. That's because sodium channels, for a small amount of time, are completely blocked off and unresponsive. As soon as those sodium channels are activated again, we can regenerate another action potential as long as there's a really high intensity stimulus. So now that those sodium channels are open back up for business, if we get a really, really high intensity stimulus, then we can regenerate another action potential during a relative refractory period. The reason we have a refractory period, as Joe alluded to earlier, is to control the amount of action potentials generated per second. Otherwise, you would fry out your nerves. they would undergo way too much activation.
Would that happen like, for say, an individual being like at war and like your response time has to be like, maybe they're put in a situation where they're like isolated and they're put in I don't know, I can't think of one right now, but like they just experience like an explosion and they're running away and they're getting shot at.
Yeah. So it's not going to change the electrophysiology of your nerves, but it's going to affect your brain negatively, meaning you're going to associate a really traumatic, that's what PTSD is. It's associated.
It just keeps.
It's like a loop. So what happens is that brain pathway, that emergency danger pathway got lit up really, really strongly one time. And now, as soon as any stimulus that's resembling that triggers that pathway, you're taken back to that situation. You feel that exact same anxiety. And you don't have to be in that situation to experience that pain or anxiety response, which is PTSD. Yeah, it's bad. All
I
right.
had a note on that. My husband works with a guy that was in Vietnam, and he said that he whistles all the time, and the guy does, and he said that a song came on the radio from like Vietnam, and he just stopped, and he said he just had this look, and he was like, Pat, he had to like kind of shake him to get him out of it, and he was like Vietnam, and he just shook his head, and it was just that one thing brought him back to where he was, and he
So it's just the proper or improper nerve got stimulated, and that caused that, involuntary nerve pathway to fire again. Yeah,
It's interesting.
it is interesting. It's bad. When we talk about impulses, we have to talk about speed of travel. So myelinated axons travel really, really, really fast. Impulses through myelinated axons. 120 meters per second is about as fast as you drive your car, faster, hopefully. Thin unmyelinated axons travel at 0.5 meters per second, which is really slow. Okay, so that tells you that this massive difference between two axons, one myelinated, one not, as that impulse jumps from node to node on the myelinated axon, we call that saltatory conduction, which means a leaping conduction. So that's how the signals travel so quickly as they leap down the axon. They're just jumping. Remember, myelin is a lipid-rich substance. It's waterproofing. It's a protective insulator around that axon wire. So it's kind of like electrical tape, right? If you have an exposed wire, wrap it in electrical tape and it insulates that wire and it will then work properly again if you wrap it correctly.
Okay, it's the Schwann cell, right?
That's the Schwann cell. Okay. We're gonna go ahead and stop there.
Was that a question?
I have a.
Yeah, so I'm gonna be gone on Friday. I'm going to a wedding. You guys gonna have a sub in lab. If he doesn't go through these 5 slides, I'll do them on Tuesday when we get back. Okay, so he'll administer your quiz. Just treat it like you would if I were there. Okay.
Why is there a gap between us and that?
Oh.
I was gonna say
Yeah.
easy.
Okay. Now everybody, not everybody, but I'm sure somebody's gonna be able to answer this properly. Okay. Why the space? I want to see if somebody just hit it right on the head. Let's go. Somebody did it. Get it.
I feel like if you don't have
Because
a
you said you
space,
had an answer
there's
last
no-
time, you said hold on.
Jamie,
to
go
that.
ahead. You go first, and then we'll.
I feel like
go
if you
around.
don't have that space, there's no way for the neurotransmitters to go anywhere. Like, they have to be kind of like osmosis in a way. Am I saying that right?
I mean, the neurotransmitters, the space isn't
And it's
for
electrical.
to hold the neurotransmitters.
So it's like, kind of
We
like
could-
lightning in your house.
We could just put them to the side, though.
If they were touching, if you were touching and you had an electrical current coming through, wouldn't you just fry the ends and then they wouldn't work anymore?
I feel like it
No,
would
because
pass
it could
through.
still be at the same voltage.
It's like touching an electrical fence and grabbing your friend. It's not going to deafen you, but it'll zap them.
Yeah, good. It's
Right.
the same. It's not going to affect the nerves. It's not going to damage them. Yeah, it's brilliant.
I think it's for allowing the free movement of the ions, because if the ions space, you're restricting the movement of those ions, so it would take a lot more energy than already for that neuron to kind of push them out. It's like, if you're in a canoe and you're already struggling, or not struggling, but you're putting a lot of energy to take out the water, someone adds more water to the space, you're gonna have to work even harder. But if you are, almost on the seabed with no water, it becomes a disadvantage because ultimately that space provides you with the medium. And if there's an issue with one of the synapses, maybe it backfires or whatever odd reason, something very abnormal happens, you don't want them too close together because then you could actually probably then get feedback. Like it could possibly travel backwards, or it could cause some very strange abnormality.
Yeah, it has nothing to do with the space or the ions. I know that sounds weird, but you guys are all good guesses. These are good guesses. Yeah.
I was just asking that it like allows for buildup of neurotransmitter that you can likelihood that a threshold would be met and then an action schedule form.
You're close with neurotransmitter. It has something to do with neurotransmitters.
Attach and release of the molecules. Like the rings that they bind and they're released
Yeah, kind of. Not quite. You're close. Anybody else?
Okay, so if you said it has to do with
It has to do
neurotransmitters,
with neurotransmitters.
so there are different types of neurotransmitters that,
Right. You're closer, warmer.
and they would have to be different types of binding sites too, with the different types of, so in order to,
Keep going.
thinking is hard, okay?
Thinking is hard.
So if there are different types of neurotransmitters and different types of
Receptors.
you would need that space in order to,
Figure out which one's
Yes.
gonna work.
yeah,
Give them the,
It allows for variability.
for
in
variability,
synapse.
right?
Does that make sense?
Yeah.
If you just had a connection, then that nerve would do the same thing as the nerve before it. But if you have a space there, you can put a different receptor there, and you can bind a different neurotransmitter to that receptor, and it allows for different combinations to happen. So you can either shut down the next nerve with this neurotransmitter, or traveling through the
Activate
space,
it.
or you can activate it, or you can partially shut it down or partially activate it. Does that make sense? Good. Okay, that's the answer. So you guys all kind of like participated to get there. Good job.
Yay! Teamwork makes the dream work.
So you guys will have a sub. I'll do everything the same way that I do it. So I'll write the quiz, and it's not going to be his quiz or anything, just so you know.
So the pace